Hello, my name is Baeksan Chang and I work on Core Audio. Today I will discuss a new way to create audio drivers with DriverKit. But first, let's review how audio drivers work today. Prior to macOS Big Sur, an audio server plugin would need to communicate with a hardware device through a user client to a kernel extension. In macOS Big Sur, the Core Audio HAL provided support to create an audio server plugin built on top of a DriverKit extension. The layer between the plugin and the DEXT was the same as with the KEXT, but security was improved by moving out of the kernel and into user space. For more information on DriverKit, please check out the previous WWDC DriverKit videos. While the current solution allows audio driver development to move out of the kernel, two separate components are still needed to implement a functional hardware audio driver: an audio server plugin and a driver extension. This complicates development, increases resources, and can increase overhead and latency. Starting in macOS Monterey, you only need a DEXT, no more plugin. AudioDriverKit is a new DriverKit framework used to write audio driver extensions alongside USB DriverKit or PCI DriverKit. This new framework handles all the inter-process communication to the Core Audio HAL. Since you only have a DEXT, now you don't need to communicate between your DEXT and an audio server plugin. You can stay focused within DriverKit. Since AudioDriverKit extensions are bundled inside a Mac app, a separate installer is no longer necessary. And now your driver is loaded immediately. No reboot required. Now that you know the benefits of AudioDriverKit, let's dive into making a new audio driver. I will start with a brief overview of the components involved in an audio driver, then cover some things you'll need before writing your DEXT. Once you're ready to start writing code, I will walk through how to configure and initialize your DEXT. Create devices, streams, and other audio objects, and deal with the I/O path and timestamps. Lastly, I will discuss how to handle configuration changes and show you a demo of the DEXT at the end. So let's start with architecture. The diagram shows how the HAL communicates with driver extensions using the AudioDriverKit framework. The AudioDriverKit framework will create a private user client that will be used for all the communication between Core Audio and your audio DEXT. This user client is not intended to be used directly and not exposed to your DEXT. Notice that there is no plugin or custom user client required to communicate between your app and DEXT. Optionally, your app can open a custom user client to communicate with your DEXT directly if needed. Now let's talk about the entitlements you will need. All DriverKit driver extensions must have the DriverKit entitlement. AudioDriverKit DEXT must also have the entitlement to allow any user client access. This is available to all developers who have been approved for any DriverKit entitlements. Additionally, any transport family entitlements should be added as necessary. If you have not yet requested a USB or PCI transport entitlement, visit Apple's developer site to submit a request. Keep in mind that the sample code presented is purely for demonstration purposes and creates a virtual audio driver that is not associated with a hardware device. And so, entitlements will not be granted for that kind of use case. If a virtual audio driver or device is all that is needed, the audio server plugin driver model should continue to be used. Now let's look at your DEXT info plist. These settings need to be added to the IOKit personalities of the DEXT. AudioDriverKit will handle creation of IO user audio driver user client required by the HAL. The HAL has the required entitlements to connect to the user client connection. Here's an example of a custom user client for simple audio driver user client. See the AudioDriverKit types header file for more information. Next, let's talk about configuration and initialization. The first step to configuring an audio DEXT is to subclass IO user audio driver and override the virtual methods. IO user audio driver is a subclass of IO service. Subclass any IO user audio objects that are needed to implement custom behavior. Then configure and add them to IO user audio driver. The diagram shows an overview of IO user audio objects you will be creating. Simple audio driver is a subclass of IO user audio driver and the entry point into the DEXT. Simple audio driver will create a simple audio device which is a subclass of IO user audio device. The audio device handles all start-stop I/O related messages, timestamps, and configuration changes. Simple audio device will create various I/O user audio objects. The device object will also create OS timer dispatch sources, OS actions, and implement a tone generator to simulate hardware interrupts and I/O. I/O user audio stream is a stream owned by the device. The stream will use an I/O memory descriptor for audio I/O, which will be mapped to the HAL. I/O user audio volume level control is a control object that takes scalar or dB values. The control value will be used to apply gain to the input audio buffer. All I/O user audio objects can have I/O user audio custom properties. Simple audio device will create an example of a custom property and a string as its qualifier and data value. Let's take a look at the code. Simple audio driver is a subclass of I/O user audio driver. Start, stop, and new user client are virtual methods from the I/O service class that the driver needs to override. Start device and stop device are I/O related virtual methods from I/O user audio driver. These will be called when the HAL starts or stops I/O for an audio device. I will discuss the I/O path after going over devices, streams, and other audio objects. The example shows how to override new user client to create user client connections. New user client will be called when a client process wants to connect to the DEXT. The AudioDriverKit framework will handle creation of the user client required by the HAL by calling new user client on the I/O user audio driver base class. This will create the I/O user audio driver user client that is needed by Core Audio HAL. A custom user client can be created as well by calling I/O service create, which will create the user client object from the driver extension's info plist entry added earlier. Let's take a look at how to override start and create a custom I/O user audio device object. First, call start on the superclass, then allocate the simple audio device and initialize it with a few required parameters. The initialized device needs to then be added to the audio driver by calling add object. Finally, register the service and the driver is ready to go. Now that your driver is initialized, let's create a device, stream, and a few other audio objects. Subclass I/O user audio device to get custom behavior. Let's create an input stream, volume control, and a custom property object. The init method for simple audio device shows how to configure the device and create various audio objects. The sample rate related information of the device is configured by calling set available sample rates and set sample rate on the device. Create an I/O buffer memory descriptor that will be passed to the I/O user audio stream. The memory will be mapped to Core Audio HAL and used for audio I/O. The memory should ideally be the same I/O memory used for DMA to hardware. I/O user audio stream is created by specifying it with input stream direction and passing in the I/O memory descriptor that was created above. A few additional things need to be configured on the stream before it is functional. The stream formats are defined by creating a format list of I/O user audio stream basic descriptions. Specify the sample rate, format ID, and the other required format properties. Set the available formats by passing in the stream format list declared above, and then set the current format of the stream. Finally, add the configured stream to the device by calling add stream. Now let's go over creating a volume level control. To create a volume control object, call the I/O user audio level control create method. The control is a settable volume control with initial level set to -6 dB and with a range of 96 dB. The element, scope, and class of the control also needs to be specified. Finally, add the control object to the device. The volume control gain value will be used in the I/O path by applying the gain to the input stream's I/O buffer. Now let's go over creating a custom property object for the device. A property address needs to be provided for every custom property object. Define a custom selector type with a global scope and main element. Next, create the custom property object by providing the property address defined above. The custom property is settable and the qualifier and data value types are both strings. Now create an OS string for the qualifier and data value, then set it on the custom property. Finally, add the custom property to the device. Now that you have created audio objects, let's talk about I/O. The get I/O memory descriptor method will return the I/O memory descriptor used by the I/O user audio stream. The I/O memory descriptor is passed into the init method when creating a stream, and the stream can be updated with a new memory descriptor as well. The memory will be mapped to the HAL and used for audio I/O. The same memory descriptor used by the stream should ideally be the same one used for DMA to the hardware device. I/O user audio clock device is the base class of I/O user audio device. Update current 0 timestamp and get current 0 timestamp should be used to handle timestamps from the hardware device. The timestamps will be handled atomically, and the HAL will use the sample time host time pair to run and synchronize I/O. It is vital to track the hardware clock's timestamps as close as possible. Let's take a look at the simple audio device class and focus on the I/O related methods. Start I/O and stop I/O will be called from the driver when the HAL is attempting to run I/O. The private methods are shown that use I/O timer dispatch source and OS action to simulate hardware interrupts, which will be used to generate 0 timestamps and audio data on the input I/O buffer. Since this example is not running against a hardware device, timers and actions are used in place of hardware interrupts and DMA. Start I/O will be called on the device object when the HAL is attempting to start I/O on the device. Any calls necessary to start I/O on the hardware should be done here. Afterwards, start I/O should be called on the base class. Next, get the input stream's I/O memory descriptor, so an I/O memory map can be created by calling create mapping. The buffer address, length, and offset will be used in the action occurred handler to generate a tone on the I/O buffer. Start timers is called to configure and enable the time sources and actions to generate timestamps and fill out the input audio buffer. Update current 0 timestamp is called to atomically update the sample time host time pair for the I/O user audio device. The timer source is enabled and set with a wake up time based on mock absolute time and host ticks configured from the device. The ZTS timer occurred action will be called based on the wake time so that a new timestamp can be updated on the device. Not shown here, but the sample code also updates the tone generation timer and action in a similar way. When the 0 timestamp action fires, the last 0 timestamp value is obtained from the device by calling get current 0 timestamp. If this is the first timestamp, use the mock absolute time passed into the timer as the anchor time. Otherwise, the timestamps are updated by the 0 timestamp period and host ticks per buffer. Calling update current 0 timestamp will update the device's timestamps so that the HAL can use the new values. Set the ZTS timer to wake up in the future for the next 0 timestamp. To simulate DMA, audio data will be written to the input I/O buffer when the timer action runs. First, check if the input memory map that was assigned when start I/O was called is valid. Use the memory map buffer length and stream format to get the length and samples for the I/O buffer. Since the stream only supports signed 16-bit PCM sample format, get the buffer address and offset and assign it as an int16 buffer pointer. Now the input I/O buffer can be filled out by generating a sine tone. First, get the input volume control gain as a scalar value, then loop for the number of samples needed and generate a sine tone, applying the volume control gain. Next, loop through the buffer and fill in the sine tone sample to the I/O buffer based on the channel count, also accounting for wraparound. Now that the audio dext is configured and can run I/O, the next step is to handle configuration changes to update the device and its I/O related state. The device methods shown can be used to request and perform configuration changes. For changes to an audio device's state that will affect I/O or its structure, the driver needs to request a config change by calling request device configuration change. The HAL will stop any running I/O and perform device configuration change will be called on the driver. Only then can the audio device update its I/O related state. A common scenario of this would be updating the audio device's current sample rate or changing the current stream format to correspond with changes to the hardware device. The diagram shows the sequence of events for device configuration changes. The driver should first request a configuration change. The HAL will notify any listeners that the config change will begin for the device. I/O will be stopped on the device if it is currently running. The current state of the device will be captured. Perform device configuration change will be called on the driver. This is when the driver is allowed to change any state on the device and hardware. Once a config change is performed, the new state of the device will be captured, and all I/O-related state, such as I/O buffers or sample rate, will be updated. Any changes to the device's state will then be notified to any client listeners. If I/O was previously running prior to the config change, I/O will be restarted on the device. Finally, the HAL will notify any listeners that the config change has now ended. To simulate a hardware bottom-up config change request, a custom user client command is used to trigger a sample rate change on the DEXT. Request device configuration change will notify the HAL of a config change request on the audio device. Notice that the change info can be any kind of OS object. This example provides a custom config change action and the change info as an OS string. To handle performing the configuration change, the simple audio device class needs to override the method perform device configuration change. In perform device configuration change, handle the config change action in the switch statement, log the same OS string object that was supplied as the change info when the config change was requested. Next, get the current sample rate and set a new rate on the device. Make sure the audio stream updates its current stream format to handle the sample rate change by calling device sample rate changed on the stream object. Other config change actions the device does not handle directly can be passed off to the base class. Let's take a look at this on the Mac. So Simple Audio is the sample code application that bundles the driver extension. To install the audio driver extension, simply press Install Driver, and that should bring up the security preferences. So if we press Allow, that should dynamically load the audio driver extension. Previously, this was not possible with the KEXT because a reboot would be required. So Simple Audio device has the sample rate formats available and the tone selection data source and the volume control we added in the sample code. Now we can open QuickTime and do audio recording on the audio device. And to test the bottom-up config changes, we can directly communicate with the DEXT to toggle the tone frequency or the sample rate, and the changes should also be reflected in audio MIDI setup. To get rid of the driver extension, simply delete the application. And you can see it is no longer available in audio MIDI setup. To wrap things up, I did a recap of the state of audio server plugins and DriverKit extensions. This will continue to be supported when the audio server plugin driver interface is not deprecated. I introduced the new AudioDriverKit framework and discussed the benefits of the new driver model. I went over an in-depth example of how to adopt the new AudioDriverKit framework and showed sample code to create an I/O user service-based audio DEXT, all running in user space. Download the latest Xcode and DriverKit SDK. Adopt AudioDriverKit for audio devices that have DriverKit-supported hardware device families. And please provide any feedback about AudioDriverKit through Apple's Feedback Assistant. Thanks.